Now we're going to answer the question, what happens to this regulator circuit when RL is outside the range on the maximum end? So this is our same circuit as previously, where we have a specified range of 50 to 250 ohms. And remember, this is RL minimum, and we saw in the previous video that when you have a resistance less than this minimum resistance in the range, you lose voltage regulation, that you no longer have VZ volts across the load. You have something less than that. Well, now we're going to look at, well, what happens when the load resistance is greater than the maximum RL in the specified range? So in this particular example, what happens when the load resistance is more than this 250 ohms? Now this is the circuit that we're going to analyze to answer this question, and notice that the Zener diode is represented as a voltage source of VZ. And it should be clear from previous discussion that the issue on the higher end of the range is not one of voltage regulation, that we will still get voltage regulation, because if you remember previously we saw that within the range the Zener diode is always conducting, and as the load resistance is greater, well, we get more reverse bias volts than what we need, more than the minimum in order to get the Zener to conduct. And that was shown in this video here with this analysis, where when RL is 50 ohms, we just had enough reverse bias voltage to get the Zener to conduct. But then when RL was 150 ohms and 250 ohms, that's when we had more than enough, right? We had 6 more reverse bias volts than what we needed here. We had 8 volts more reverse bias voltage than what we needed here. So you see, when you're outside the range on the maximum side, the Zener diode is still going to conduct in the reverse bias direction, and it's going to be acting like a voltage source of VZ. Alright, so the issue is something different than losing voltage regulation like you do on the minimum side. Alright, so let's see what that is, and to see what the issue is, you can see that I defined some currents here. Also, doing a general example now using variables instead of numbers, okay, just to come up with some general expressions here for the currents. And that's where we're going to start. We're going to write equations for each one of these currents. This is the source current through RS, and using Ohm's law, that source current would just be Vs minus Vz, right? Because the voltage across RS, which is the difference of the voltage on one side compared to the other side, right? And since current's flowing like this, we take Vs minus Vz as our voltage difference, and then divided by RS. Okay, so that's our equation for IS. Then we have IRL. Okay, IRL is just going to be VZ, the voltage across RL. Okay, divided by RL. Now, the Zener current, we can't get the Zener current with Ohm's law, but we can get the Zener current just applying KCL here to this node, that we got IS flowing in. Both IZ and IRL are flowing out of this top node. Again, diodes always absorb power, so current's going to flow from the higher voltage end to the lower voltage end. So that's the correct direction for IZ. So IZ, the Zener current's just going to be IS minus IRL. Alright, so these are our 3 equations for these 3 currents in the circuit. Now, let's think about, well, when RL increases, okay, because that's what we're looking at here, is what's going to happen when RL is greater than RLmax, right? So RL is increasing here, past the value 250 ohms. So let's see what happens to these currents as RL increases. Well, IS is just going to remain the same, right? IS doesn't have a dependency on RL, right? We got a fixed amount of voltage on this side of RS, and we have a fixed amount of voltage on the other side of RS. So there's a constant amount of voltage across this resistor RS where the current IS is flowing through. So this just remains constant. Okay, your source current here is constant. So as RL increases, nothing's going to happen to the source current. It's just going to remain what it is. Okay, now IRL, well, clearly there's a dependency there on RL, and VZ is a fixed amount. So as RL increases, IRL is going to be decreasing. Okay, so IS is constant, IRL is going to be increasing as RL is, IRL is going to be decreasing as RL is increasing. Alright, so now, and this is really the important one here, what's happening to this Zener current as RL increases? Well, IS is constant like we said before, and IRL is decreasing with increasing RL. So this must mean that the Zener current is increasing as RL increases. And you see, this is the issue, is that the amount of power the Zener is absorbing, okay, the amount of power that it's dissipating, is going to be equal to its voltage VZ times its current IZ, right? And VZ is just a constant amount. As RL increases, IZ is increasing, therefore the power that's being dissipated by the Zener, okay, what's being absorbed by the Zener, is increasing. You see, as IZ increases, the power for the Zener increases. So the issue is you're worried about the Zener frying, the Zener burning up. Okay, we already mentioned that on spec sheets, on data sheets, for Zeners you have a VZ, right? Also on a spec sheet for Zener you have PZ max, right? And PZ max is a power rating. Okay, that's the most power the Zener can handle without being physically harmed. Okay, so if you exceed the power rating, you're going to likely damage the Zener diode. It's going to burn up and then it's going to become defective. So you see, that's the issue, is you want to make sure when RL is greater than RL max, you know, you want to make sure that your Zener diode is not going to fry. That's what sets this value, is making sure the Zener is safe from burning up. So let's look at an example for calculating RL max. So let's say we have this circuit here. In fact, this is the same circuit that we used to calculate RL minimum in the previous video. So on the data sheet, VZ is given as 10 volts and PZ max is given as 50 milliwatts. And we want to find what RL max is. So you see, RL, using Ohm's law, it's going to be the voltage across it divided by the current through it. Well, the voltage across it's just VZ, because again the load is in parallel with that Zener diode, right? So this is just going to be 10 volts. So you see, what we need to do is we need to find what IRL is. Okay, and just like we had in the general example, okay, our currents, okay, this is IS, this is IZ, and this here is IRL. Okay, so once we get IRL from Ohm's law, we can go ahead and calculate what RL max is going to be. So let's get IS. Remember, IS is a constant amount with RL as RL changes. Well, IS in this problem, it's just going to be 18 minus 10 over 1K, which is 8 milliamps. Okay, and now we want to get IZ. Yeah, and this will be the maximum IZ that we obtain from PZ max. Okay, so you see PZ max divided by VZ. Okay, so IZ max in this problem is just going to be 50 milliwatts divided by 10 volts, and that will come out to, excuse me, that comes out to 5 milliamps. Okay, so that's our IS, that's our IZ. IRL using KCL is just going to be 8 minus 5, which is 3 milliamps. And now RL, right, 10 volts divided by 3 milliamps. That comes out to 3 1/3 k ohms. Okay, so that's how you go about calculating RL max. Now, this calculation here, okay, was assuming no safety factor. Okay, SF here stands for safety factor. Okay, what a safety factor is that it's not a good idea to operate a component right at its maximum capability. See, this RL max is based on using the PZ max value of 50 milliwatts, but in good designs, we never operate a component right to its maximum capability. We always put a buffer in, okay, which is called a safety factor. So for example, if we had a safety factor in this problem of 2, and usually you'll have a safety factor of at least 2, okay, often it's more than that, okay, a bigger safety factor. Well, if we use a safety factor of 2, that means that we essentially are going to use a PZ max, okay, I'll call it PZ max prime. Okay, that's half what our true PZ max is. So you see, here we use the PZ max right off the data sheet of 50 milliwatts. If we have a safety factor of 2, we just take that data sheet PZ max and divide by the safety factor, and now we would use a PZ max of 25 milliwatts. So using a safety factor of 2, this is how it would change our analysis. See, it's not going to affect IS, okay, because IS, again, is just this constant amount, so the safety factor doesn't affect that at all. The safety factor doesn't change how we calculate RL. It's still the voltage across the RL divided by the current through RL. But you see, what's going to change because of the safety factor is the value of IRL, because when we change the safety factor, the maximum Zener current that we use is going to be different. So you see, that's where you start as far as when you're doing a problem using a safety factor compared to the problem that didn't use a safety factor, is now you're going to have a different IZ max than what you had previously. See, now this is going to be 25 milliwatts divided by 10 volts, which is 2.5 milliamps, excuse me. Okay, so now your IRL is going to be different because now it's the source current 8 minus 2.5, which is 5.5 milliamps. And now RL will be 10 volts divided by that current 5.5 milliamps. And this comes out to roughly 1800 ohms. Actually, it's 1818 ohms. Oops. Okay, ohms. Sorry for squeezing that in. Okay, so 1818 ohms is the new RL max. Remember, this is RL max here. Okay, so with the safety factor, you can see the RLmax is much less. It's 1800 ohms compared to 3333 ohms. Okay, so this is how you calculate RLmax, both with a safety factor, without a safety factor, and with a safety factor.